Hello students, this video lecture will cover section 8.2, special right triangles. And our goal for this lesson is to be able to use the properties of 45, 45, 90 and 30, 60, 90 right triangles. First we're going to discuss the properties of a 45, 45, 90 right triangle. So a very important formula here says that the hypotenuse equals the square root of 2 times the length of a leg. And in this case, since this is a 45, 45, 90 right triangle, we know that this triangle is also isosceles. So here we have two legs that are of the same length. So it doesn't matter which leg you use in this formula, you end up with the same result. So our first question says, what's the length of the hypotenuse of a 45, 45, 90 triangle that has a leg length of 5 times the square root of 3? So the first thing we're going to do here is draw a right triangle. So here we have a picture of a right triangle. We know that it's a special right triangle. It's a 45, 45, 90 right triangle. We know that the leg length is 5 times the square root of 3. So that's the length of both legs based on the converse of the isosceles triangle theorem. And based on the previous slide, we know that the length of the hypotenuse equals the leg length times the square root of 2. And so this is our special rule for 45, 45, 90 triangles. So we can substitute into this equation. We can call this C if we want. So C, the length of the hypotenuse, equals the length of the leg, which is 5 times the square root of 3, times the square root of 2. And so in order to continue, we need to know the special rule for multiplying square roots. So just as a little aside, let's go ahead and discuss that. If we have the square root of A, and we want to multiply that by the square root of B, this is the same as the square root of A times B. So this is a very important rule to remember. So in this case, the length of C equals 5 times the square root of 3 times 2. And then C must equal 5 times the square root of 6. So this length is 5 times the square root of 6. And based on what we learned in section 8.1, we could use the Pythagorean theorem in order to check this answer. So a second type of question will give us the length of the hypotenuse and ask us to find the length of a leg. So again, a good place to start is with a diagram. So here we have our 45, 45, 90 right triangle, and we know that the length of the hypotenuse is 10. And so we're trying to determine the length of the leg here. And we're going to use that same formula. The hypotenuse equals the length of the leg times the square root of 2. And we're going to substitute into this formula. So the hypotenuse here is 10. So this equals the length of the leg times the square root of 2. So in order to solve this, we want to divide both sides by the square root of 2 to get the L all by itself. So these two cancel. And we get L equals 10 divided by the square root of 2. Now, this causes a little bit of a problem, because typically we don't leave square roots in the denominator. So here we want to use a technique called rationalizing the denominator. What we want to do is we want to multiply this by 1. But we want to multiply by 1 in a very special way. So instead of just multiplying by 1, I'm going to multiply by the square root of 2 over the square root of 2. And so whatever the square root is in the denominator, we're going to multiply top and bottom by that. So what we have is on top we have 10 times the square root of 2. And on bottom we have the square root of 2 times the square root of 2. So the top doesn't simplify at all, so we have 10 times the square root of 2. The rule for the bottom we talked about on the previous slide. It can be written as the square root of 2 times 2. So 2 times 2 is 4. So we have 10 times the square root of 2 on top. We have the square root of 4 on bottom. So the square root of 4 is 2, so we have 10 times the square root of 2 on top. We have 2 on bottom. And 10 divided by 2 is 5, so our final answer here is 5 times the square root of 2. So the length of the leg in this case is 5 square root of 2. So here again we have a word problem. We're planning on building a path along one diagonal of a 100 foot by 100 foot square garden. And we want to know to the nearest foot how long that path will be. Let's go ahead and mark our diagram. We know that this is 100 feet, and we know that since it's a square, all the sides are 100 feet. And so let's go ahead and mark our path. It's going to start at one of the corners and go to the other corner. Now, what's actually interesting about this question is the rest of the garden then we actually don't need. We can pretend like the rest of this garden doesn't even exist. Well, since we know this was a square garden to start with, we know that all of the angles are right angles, so we know that this is a special type of triangle. It's a right triangle. And since these two sides are both 100 feet, we know that this is an isosceles right triangle, so we know that the base angles have to be congruent. So that's how we know that this is a 45, 45, 90 right triangle. Now, using our special rule, we know that the hypotenuse has to equal the leg times the square root of 2. So in this case, the hypotenuse has to be 100 times the square root of 2. And since we're trying to determine this to the nearest foot, we can just plug this into our calculator. So when we plug this into our calculator, we get approximately 141.42. And if we're rounding this to the nearest foot, all we have to do is look one spot to the right. And since that's a 4, we know that this is about 141 feet. So our second type of special right triangle is a 30, 60, 90 triangle. So in a 30, 60, 90 triangle, the length of the hypotenuse is twice the length of the shorter leg. And the length of the longer of the two legs is the square root of 3 times the length of the shorter leg. So let's actually prove this. If we take this bottom side, which is of length s, and extend it so that it goes to the opposite side of the triangle, we get the picture shown here. By setting our compass to the length of this longer side, we can make sure that we get two sides of equal length if we draw the arc across the bottom of the triangle. So now let's connect the top to this section that we've just seen. Thinking back to what we know about congruent triangles, we've forced these two sides to be congruent by using our compass to measure that distance. We know that this side down the middle is the same in each of the two triangles. And we know that since we made this line straight, these are both right angles. So here we have two triangles that are congruent by hypotenuse leg. Since the two triangles are congruent, CPCTC tells me that this has to be a 60-degree angle. And so the connection of the two triangles has to be an equilateral triangle. This has to also be a 60-degree angle. Also, by CPCTC, I know that this side has to be of length s. So the entire distance here has to be 2 times s. And since this is an equilateral triangle, we know that this side is also 2s. So we've verified one part of the formula, and that is that the hypotenuse equals 2 times the shorter leg. To show the length of the longer leg, I'm going to use the Pythagorean theorem. So here, I know that the shorter leg squared plus the length of the longer leg squared has to measure the length of the hypotenuse squared. So through simplification, we have s squared plus l squared has to equal 2 squared, which is 4, times s squared. So we subtract s squared from both sides. That cancels on the left-hand side, and we get that l squared has to equal, we have 4s squared, subtract 1s squared, that gives us 3s squared. We take the square root of the left-hand side, we get l. We take the square root of the right-hand side, we get the square root of 3 times s squared. The square root of s squared is just s, so we get l equals s times the square root of 3. And that verifies the second part of our formula. So question number 4 gives us the value of one side and asks us to find the values of both d and f. Well, let's start by writing our two formulas. We have h equals 2 times s, and we have the length of the long leg equals the length of the short leg times the square root of 3. Let's go ahead and plug in what we know. The hypotenuse here is f, so we know that f equals 2 times the shorter of the two legs. And remember, the shorter leg has to be opposite the smallest angle, so f equals 2 times d. And here the longer leg, or 5, has to equal the shorter leg, d, times the square root of 3. If we look here, we have two variables, f and d, in the left-hand equation, and only a single variable in the right-hand equation. So we can solve for d by dividing both sides by the square root of 3. So the square root of 3's cancel. We get d equals 5 over the square root of 3. And so we need to rationalize the denominator. Multiply both top and bottom by the square root of 3. This is going to equal 5 times the square root of 3 on top. And square root of 3 times the square root of 3 is going to be the square root of 9, which is 3. So d in this case is going to equal 5 times the square root of 3 over 3. And so we're going to substitute that into the other equation. We have f, which equals 2 times d, so we have 2 times 5 times the square root of 3 divided by 3. So we multiply the top, 2 times 5, so f is going to equal 10 times the square root of 3, and that's all divided by 3. So here are our values of d and f. So in this case, our final question is a word problem. We have an artisan that makes pendants in the shape of equilateral triangles. And supposing the sides of a pendant are 18 millimeters long, we want to know the height of the pendant to the nearest tenth of a millimeter. So the first thing I like to do with this type of question is orient my pendant correctly. So I'll separate the triangle here, and I'll reorient it so that the base is parallel to the bottom of the screen. Now we've been told that all the side lengths are 18 millimeters. We also know that this is an equilateral triangle, so we know that all the angles are 60, 60, 60. Well, let's go ahead and draw in a height in this case. So once we have the height, we can see that we're actually only going to deal with half the triangle. So let's draw that. So here we have half the triangle. We know that this is a 60-degree angle. We know that this is 30 based on triangle angle sum. We know that this is 18. And since we've split the base of the triangle in half, we know that that's 9. Using our special rules for 30, 60, 90 triangles, we know that the long leg has to equal the short leg times the square root of 3. So the long leg in this case has to equal the short leg, which we know is 9 times the square root of 3. And since we're asked to round to the nearest tenth of a millimeter, we can just plug this into our calculator. And so we know that L is about 15.588. And since we're rounding to the nearest tenth, we look at the hundredths position, and we find that the height of this is about 15.6. So to the nearest tenth of a millimeter, we know that L is about 15.6 millimeters. That concludes this video lecture on Section 8.2, Special Right Triangles. Hopefully you can now use the properties of 45, 45, 90 and 30, 60, 90 right triangles. Thanks for your attention, and I'll see you soon.